Let's continue data preparation phase. So far we have considered purely random sampling methods. While we've been using purely random sampling methods for splitting the data, this approach can introduce sampling bias if our dataset is too small. In smaller datasets, random sampling might not adequately represent the overall population, potentially skewing results. This can lead to models that don't generalize well to new, unseen data. To mitigate this risk, especially in smaller datasets, we might consider stratified sampling. This ensures that each subgroup or category is proportionally represented in both the training and test sets, leading to more reliable outcomes. For example, consider the U.S. population, which consists of approximately 51.1% females and 48.9% males. A well-conducted survey should aim to maintain this ratio in the sample, collecting around 511 females and 489 males, especially if responses might vary across genders. This approach is known as stratified sampling. In this method, the population is divided into homogeneous subgroups or strata. We then sample a proportional number of instances from each stratum, ensuring that the test set accurately represents the overall population. This helps to prevent sampling bias and enhances the reliability of our model's predictions. Examining the histogram for median income reveals that most values cluster between 1.5 and 6, representing 15,000 to 60,000. However, there are some instances with median incomes that exceed 6. It's crucial to ensure that there are enough instances in each stratum to avoid bias in estimating the importance of a stratum. If certain strata are underrepresented, our understanding of their significance can be skewed, potentially leading to inaccurate model predictions and interpretations. The following code demonstrates how to use the PD-cut function to create a new attribute for income categories, dividing the values into 5 categories labeled from 1 to 5. In this example, Category 1 includes income values from 0 to 1.5, less than $15,000. Category 2 ranges from 1.5 to 3. Categories 3, 4, and 5 continue accordingly. This categorization allows for easier analysis and modeling based on defined income brackets. The following code visualizes the distribution of the income categories in the dataset using a bar chart. In this code, value_counts counts the occurrences of each income category. Sort_index sorts the categories in ascending order. Plot.bar creates a bar chart with categories on the x-axis and the number of districts on the y-axis. Labels for the axes are added for clarity. The resulting bar chart displays the distribution of districts across the defined income categories, allowing for an easy visualization of how many districts fall into each income bracket. You're now prepared to implement stratified sampling based on the income category. Scikit-learn offers various splitter classes within the sklearn.model_selection package to assist in splitting datasets into training and testing sets. For stratified sampling, there's an efficient method using the train_test_split function by specifying the stratify argument. This allows you to create a training and test set while maintaining the same distribution of income categories in both sets. Here's how you can do it. In this example, stratify equals housing income_cat ensures that the splits in the training and test sets reflect the distribution of income categories in the original dataset. This helps prevent sampling bias and ensures a more representative dataset. To verify the effectiveness of stratified sampling, we can compare the income category proportions in the overall dataset with those in the test set. You can visualize this comparison using a bar chart or similar plot. Here's what you might observe. Stratified sampling test set. The proportions of income categories in this test set will be nearly identical to those in the full dataset. This indicates that the sampling method successfully maintained the original distribution. Random sampling test set. In contrast, the test set generated through purely random sampling may show skewed proportions, failing to accurately represent the income categories of the overall dataset.
Now let's change the topic. We will talk about critical topic in machine learning, overfitting and underfitting. Understanding these concepts is essential for anyone looking to build effective predictive models. Let's start with overfitting. Overfitting occurs when our model learns not just the underlying patterns in the training data, but also the noise and random fluctuations. This leads to a model that performs exceptionally well on the training set but struggles on unseen data. Imagine a student who memorizes answers to questions without truly understanding the material. When faced with new questions, they falter. Similarly, overfitted models can show impressive accuracy during training, but when tested with validation data, their performance drops significantly. Now, let's turn our attention to underfitting. This happens when our model is too simplistic to capture the underlying relationships in the data. An underfitted model performs poorly not just on unseen data, but also on the training data itself. Think of a student who hasn't studied enough. They miss important concepts and, as a result, perform poorly on both practice tests and exams. Just like that, underfitting leads to high bias and a lack of complexity in our models. Striking the right balance between overfitting and underfitting is crucial for developing robust machine learning models. Techniques such as regularization, cross-validation, and selecting appropriate model complexity can assist us in achieving this balance. As you embark on your machine learning journey, keep these concepts in mind. They are foundational to building models that not only fit our training data well, but also perform accurately on unseen data. Next, let's discuss how to identify overfitting and underfitting. Let's start with overfitting. Here are some signs to look out for. High training accuracy, low validation accuracy. If your model does really well on the training data but struggles on the validation data, this is a red flag for overfitting. Decreasing training loss, increasing validation loss. You might notice that the training loss keeps going down while the validation loss starts to go up. This shows that the model is learning the training data too closely and not generalizing well. Now let's discuss underfitting. Here are its signs. Low accuracy on both training and validation sets. If your model is performing poorly on both training and validation data, it's a sign that it's too simple to capture the patterns. High training and validation loss values. If you see high loss values for both training and validation sets, this means the model isn't learning effectively, leading to underfitting. Recognizing these signs will help you improve your models. Thank you for joining us today, and keep learning as you explore machine learning. In the next video, we will learn next machine learning step, model development and evaluation. See you in the next video.